Hey there. In this video, we're going to talk about Gaussian quadrature, which takes the techniques we've learned so far and turns it up to 11. It really gives you basically the best numerical integrator. First thing we need to do is learn how to change limits for our integral. We want to remap our limits, whatever they may actually be, into the range -1 to 1, because there's a lot of niceties to having those particular limits. So the way you change limits is actually not hard at all, because integrals are linear. It means you can add them together without having to do anything more complicated than add them. So suppose that we are given a problem, integration from a to b of some function g of y dy. And I want to write that in a nicer form, integration -1 to 1 f of x dx. I can accomplish that by doing a change of variables, literally a U-Substitution, although I'll do different symbols here. So I want to replace y with mx plus c, which should look just like the equation for a line. And what these two terms represent is that c will shift our integration to the left or to the right. And as you can imagine, it doesn't really matter if you pick up the integral and slide it left or right. As long as you slide the function with it, it doesn't change anything. And m here is a scaling factor that shrinks or grows the integration range. And together they will let you map any set of limits into -1 to 1. I guess any except infinite limits. Although there are actually closely related tricks to this, where you remap using a new function to get rid of the integration, like using 1 on 1 minus x. In any case, tricks like this will let you remap. So if we plug in the limits, so we do say the upper limit b is going to be equal to m times 1, which is m plus c, and the lower limit a is equal to -1 times m, so that's -m plus c. And that's two equations with two unknowns. Easy enough to solve these. We get m is equal to b minus a on 2, and c is equal to b plus a on 2. So putting those back into the original equation, the mapping we want to use here is to replace our integration variable y in the original integral with b minus a on 2 times x plus b plus a on 2. And then we also have to change dy if we do a substitution like this. dy would just be b minus a on 2. And so then this will map any finite limits into the range -1 to 1. So with that out of the way, we're now ready to set up our Gaussian quadrature. So Gaussian quadrature says, take some generic integral, and we can always remap our limits to be -1 to 1. That would be equivalent, at least approximately equivalent, to doing a summation, having n terms in the summation, where we have some weighting factor w, so some number that weights how important the function is at each point. So for example, we saw with the trapezoidal rule that we had h on 2 times f at the lower limit, in this case that would be -1, plus h on 2 times f at the upper limit. So that's an example of this kind of rule. Now that's only two terms, and so it's not great. Simpson's rule would be the equivalent of having 3 terms. It's kind of just a different way of writing out those two rules. And so you can imagine we could do higher order polynomials corresponding to higher n. But we can actually even do better than that, because doing polynomials where you have some fixed spacing point to point to point, that only gives you n degrees of freedom. And so that would match really well functions that were like n degree polynomials or n minus 1 degree polynomials. But not only can we adjust w, but we can adjust where are the sample points. And in doing that, that gives us another n degrees of freedom. So our total degrees of freedom are 2n. I should not try to write in highlighter, okay? So we have 2n degrees of freedom, which means that this is exact, not just approximate, but exact whenever f of x is of degree 2n minus 1 or less. And it doesn't need a very large n to do a very wiggly function. So even if your function f of x is not exactly a polynomial, as long as you can approximate it as a polynomial, your integration is as good as your approximation. And if you put in n equals 20, well, gosh, it's 39th order polynomial. That's basically anything you can dream up. And that's not very many points at all. I mean, we were talking about 10 to the 4 and 10 to the 8 points with Simpson's rule and trapezoidal rule, and now we're down to like 20. So this is a huge help. Now, of course, the price we have to pay is how do we find out what the weights w and the points xi actually are. So rather than just diving headfirst into a lot of hard math to try to prove this generically, I think the best approach here would be to sort of prove by example. We'll do a simple example and then talk about generically what the results are. So my simpler example is going to be, imagine that our function is a third degree polynomial. Any third degree polynomial, not even just a specific one, but any third degree polynomial. That implies that I need 2 points to exactly recreate its value with this technique. Why 2 points? Because 2n minus 1 is 3 to match the third degree polynomial. If you're wondering about that minus 1, it's because to describe a polynomial, you need an extra value to correspond to the constant term. So a third order polynomial has 4 unknowns, the coefficient for x cubed, x squared, x, and also the constant, total of 4. So our task here is to solve for wi and xi. And this is basically what you do, or this, not even basically, this is Gaussian quadrature. If I didn't mention this already, quadrature is an old name for integration. This was derived back in the day, long before computers, like over 100 years before there were computers, where people were wondering how to do integrals that didn't have a closed form solution, where you'd have to approximate the value. And there are different techniques. My favorite technique was actually to draw the function on paper, cut it out, and then weigh the paper to try to figure out how much paper you had. But this one works as well. So you can, by hand, calculate with a reasonable number of points, like 10 points or something. And yeah, maybe it would take you all day, but then you would have an actually very accurate answer to an integral that doesn't have a nice analytic solution. Anyway, we're going to do 2 points. Okay, so if on the left-hand side we have the actual integration, so we'll call our coefficients a's. So we'll have a3x cubed plus a2x squared, a1x, and a0. So that's the actual integration. And then on the right-hand side, we're going to have the summation. So we'll have w1 times x1, or f at x1, and f at x1 is equal to a3 x13 plus a2 x12 plus a1 x1 a0, and then we have w2 times f at x2, so that f at x2 would be equal to a3 x2 squared plus a2, well, that should be x3, sorry, a3 x2 cubed, a2 x2 squared plus a1 x2 plus a0. You don't understand the pressure of writing this out while being recorded. It's so easy to drop a 2 over 3. And I know like everyone in the world will come and yell at me when I do that. So if you see something that looks backwards, it probably is because I actually wrote it backwards. Okay, in any case, what we're doing now is this should be exact and we should be able to solve it. So the integration part is pretty easy to do. Since our interval is from -1 to 1, we know that any odd integrand is just going to give you 0 after you integrate it. That's part of why we wanted these limits. So this term and that term doesn't give us anything. And we end up with, on the left-hand side, 2/3 a squared plus 2a0. Right now it looks like we have one equation and 4 unknowns. It seems impossible, but actually this is 4 equations with 4 unknowns. How do I know that? Well, because we never actually said what polynomial we were doing. We're doing all third-order polynomials. And that means no matter what the numbers are for a0 through a3, this equation has to still be true. So what that means is that the equations here for a0, let me highlight it. Any terms with an a0 in it, that gives you an equation. And that equation says that w1 plus w2 is equal to 2. Because we have the term w1 a0 plus w2 a0 equals 2 a0. Sort of independent of whatever the other variables are doing, this has to always be true for all values. So that is a single equation. We also get an equation for a1, and an equation for a2, and an equation for a3. So hiding in here are actually 4 equations. So if we write out the other equations, and they all follow the same kind of pattern, we've got a w1 x1 plus w2 x2. That would be equal to 0. We have w1 x1 squared plus w2 x2 squared is equal to 2/3. And then the last one, w1 x1 cubed plus w2 x2 cubed is equal to 0. So here we have 4 equations with 4 unknowns. Now unfortunately they're nonlinear equations. That's what makes this hard. But with just having 2 points, we can get through this by hand. And the way I'm going to do this is I'm going to exploit the fact that our answer here has to be symmetric. We took our function f, right? And our function f might look something like this. And we took the mirror image of that function. Both of those, I mean, I know my drawings aren't very good. We took the mirror, I can't do it. Okay, I took the mirror image of that. Both of those have to have the same integral. So since they're symmetric, that means that whatever x1 is, x2 just has to be the negative value of that. Let's say that x1's the negative one. So if we had like negative 1/2 for x1, x2 would have to be positive 1/2. They have to be symmetric around 0. Okay, so symmetry here is going to imply that we could just use x and let that be negative x1 be the same thing as x2. Likewise, the weights for these would have to be symmetric. There's nothing special about left versus right. So whatever the weight for 1 was would have to be the same as the weight for 2. And so this is really powerful when we only have 2 unknowns. When we start getting up to like 20, things still have to be symmetric, but that doesn't mean that all the weights are the same. It just means that half the weights are the same as the other half of the weights. Okay, nonetheless, with these values, we can come back to our equation here and start plugging things in. Like for example, the first equation is going to become 2w equals 2. Tells me right away that the weight is 1. For more points, weights will differ from 1. We just know that the sum of all the weights has to be 2. Has to be the whole interval. But in this case, with only 2 points, it's 1 and 1. We can then go and look at the next equation down. Or not the next, but the third one in my list here. And that's going to say that plugging in w equals 1 tells me that 2x squared is equal to 2/3, which tells me then that x has to be equal to plus or minus, this is fine, square root 1/3, or 1 on square root 3. So in general, there's going to be some kind of pattern you get to these values. And I have to admit, I didn't prove what this pattern is going to be. I'm just showing you an example of it. But the general pattern you get if you do this generically for any n's is that each xi is not at some arbitrary location, but is instead equal to the ith root of something called a Legendre polynomial. So where n here corresponds to the number of points we're using. So in this case, if you look up Legendre polynomial P2, you will find that it has roots, that means places where it's equal to 0, that are at negative 1/3 and 1/3. The powerful thing about the Legendre polynomials is that these polynomials have roots that are all real numbers, and the roots are all in the range -1 to 1, which, hey, it's exactly corresponds to the interval we're using. The weights are not all going to be 1 always, or nice numbers always, but they are you can calculate them. They're going to be equal to 2 divided by 1 plus xi squared, and then take the derivative of the Legendre polynomial evaluated at the location of the root, the -2. So it's not beautiful, but it's also not really all that hard. What you need to get your hands on is a table of what are the roots of the Legendre polynomials. And back in the day, people would just calculate them by hand. And if you're wondering, how do you do that? You do it by doing a numerical integration. So, you know, it sort of feels chicken and egg, but once you've done it, you make a big table of all these roots to the Legendre polynomials, and you just look them up. And that's very, very fast for a computer. So let's try it out. Now what we're actually going to use out of SciPy is named quad for quadrature. To be upfront about things, this is not exactly Gaussian quadrature that is used. It's a very, very closely related technique called Clenshaw-Curtis quadrature that uses slightly different functions. So Gaussian quadrature is based around Legendre polynomials. Clenshaw-Curtis quadrature is based around Chebyshev polynomials. And the difference here is, even though Gaussian quadrature is actually better on paper, Clenshaw-Curtis works out better in practice because it's easier to calculate error estimates with Clenshaw-Curtis. You waste a lot of computer time trying to evaluate the error with Gaussian quadrature to make it so that you really wouldn't get a very good error estimate without wasting the time and really wasting this elegant method that we just put together. So Clenshaw-Curtis is slightly less accurate than Gaussian quadrature, but it's relatively easy to estimate the errors, and so that's what's used in practice. Now, we don't really need to worry too much about the nitty-gritty of it. Let's just look at the arguments to our function here. So quad wants a function, lower limit, upper limit. These can be infinite. If you want an infinite limit, it's np.inf. I'll show you an example. And you'll notice here this eps abs and eps rel, that's your desired error. The way this function works is it tries with a small number of steps in the integration, checks to see what the error is. If it's not big enough, it adds more steps. That's not as wasteful as you think, because it just sort of inserts them in between. That's the beauty of the Clenshaw-Curtis quadrature, is you can just add steps in between and not have to throw anything away. So it just adds points until it gets to the requested error. You never have to change these in practice, I found, but they're there if you have some very special case where you do need to control the error. Okay, so let's make something to integrate. Let's add a cell up here, and we'll just call it func. We'll do a real easy one to start with. We'll do just x squared. You know, we could do this one in our head. So integrate quad, we want to give it the function that we're calling. The lower limit, let's make the lower limit 0. The upper limit, let's make it 1. We don't have to tell it how many steps we want because it picks for us to get the required error. This is going to return a tuple of values, the value of the integration, and it's also going to return the error estimate. So your typical calling statement here is going to use tuple unpacking to get both I and the error, and then we can print those out. So let's print I plus or minus error. Oh, and I forgot to define my function. Shame on me. Okay, so there we go. The integration, like we could have done in our head, is 1/3 plus or minus something around 10 to the minus 15. So even though we said, hey, you need to be at least within 10 to the minus 8, that's the default, it is often far, far better than that, just because these kinds of quadrature routines are just so super efficient at evaluating smooth integrals. The one place that the quadrature type functions are going to fail on you is if you have a super noisy function, in which case they aren't any better than trapezoidal. But in physics, you usually don't have that kind of thing. So usually this is going to be your go-to. Let's look at something where we have an infinite range. So let's make a new func2 of x. And I accidentally ran the cell before I was done typing. And let's make something that's kind of like a normal distribution. So we're going to return numpy dot the exponential negative x squared. So when you plot this, it kind of looks like a bell curve. Okay, so that's our function, and then we're going to do I comma air is equal to integrate.quad. Func2 will go from 0 to infinity. So I do that with an np.inf. I can't really get the documentation if it's in there, but that's just how you represent infinity or an infinite range in NumPy. And so quad here is smart enough to check for that, and if it sees it, it does some tricks behind the scene to basically rescale the interval. If you remember, just a little bit ago, we talked about rescaling any integration range to -1 to 1. It does something along those lines to rescale an infinite range into a finite range. So if we run that, oh, forgot to print. Let's just copy our print statement. If we run that, we get an answer plus or minus something that is better than the error or smaller, I should say, than the error we asked for.